April 17th, 1916. Skies above Verdun, France. The hand gripping the control stick trembled with frustration as Lieutenant Georges Guynemer banked his Nieuport 11 Bébé fighter sharply to the left. His sixth burst of ammunition had just sailed harmlessly behind the German Fokker E.III. Words formed under his breath that would have scandalized his instructors at Saint-Cyr. Frustration that echoed across Allied squadrons where pilots were discovering a maddening truth about aerial combat. Direct aim meant certain miss. Through the open cockpit, wind tearing at his scarf, Guynemer had fired approximately 250 rounds during this engagement. The Hotchkiss machine gun had functioned perfectly. His aim had seemed true each time. Yet the German aircraft continued flying, undamaged, now disappearing into a convenient cloud bank. The mathematics of aerial gunnery were revealing a disturbing reality that contradicted everything taught in training. Official records from the French aviation militaire would later document that during the first half of 1916, experienced pilots expended an average of 7,000 to 11,000 rounds for each enemy aircraft destroyed. The wastage was staggering. Nearly 99% of ammunition fired failed to strike its intended target. Britain's Royal Flying Corps reported similar findings, with new pilots missing their targets entirely in approximately 97% of firing opportunities during their first combat missions. The problem was fundamental. At closure rates often exceeding 250 miles per hour, a bullet fired directly at an enemy aircraft would arrive at the target point several seconds after the target had passed through that space. Captain Eddie Rickenbacker, who would later command the 94th Hat in the Ring Squadron, described this realization in his post-war memoir as the moment aerial combat truly began. "We were fighting against both the enemy and physics itself," wrote British ace Albert Ball in correspondence dated June 1916. "I watched my tracers pass harmlessly behind a German scout despite perfect alignment through my sights. The revelation came suddenly. I needed to aim at empty space, not at the aircraft itself." This counterintuitive concept contradicted millennia of hunting and combat experience. Since the first thrown spear, warriors had aimed directly at their targets. Even artillery officers compensated for gravity's drop, but not for lateral movement. Now pilots faced a three-dimensional problem involving two objects moving at high speed along different vectors. The earliest attempts at solution were crude approximations. French ace Charles Nungesser developed a personal system he called the ghost aircraft method, mentally projecting where the enemy would be when his bullets arrived. Others used improvised techniques like counting ahead, allowing one aircraft length of lead for every 50 miles per hour of crossing speed, a rule-of-thumb calculation performed in split seconds while also flying the aircraft and avoiding enemy fire. The problem became even more complex when accounting for gravity, wind drift, and the ballistic properties of machine gun ammunition. The standard .303 Vickers round fired from British aircraft travelled at approximately 2,700 feet per second initially, but slowed considerably over distance. A pilot needed to judge not only the enemy's future position, but also how much his bullets would drop during flight. Lieutenant William Fry of the Royal Naval Air Service calculated that at a 45-degree deflection angle, a bullet required approximately 0.25 seconds to reach a target at 200 yards. During those 0.25 seconds, an enemy aircraft traveling at 100 miles per hour would move 36 feet, more than the entire wingspan of most combat aircraft. Aiming directly guaranteed missing. By late 1916, training schools had begun teaching rudimentary deflection shooting techniques, but implementation remained inconsistent. German pilots, who often benefited from more extensive pre-flight gunnery training than their Allied counterparts, showed higher initial hit probabilities, a difference that would narrow as the war progressed. The transformation had begun. What pilots needed next were mechanical solutions to an impossible mental calculation problem, systems that could compute the complex trigonometry of interception automatically, while pilots focused on flying and surviving. The era of instinctive shooting was ending. The age of calculated deflection was about to begin. August 3rd, 1917. Gosport Flying School, Hampshire, England. Captain Henry Adlam stood beneath the wing of his Bristol F-2B fighter, using a chalk stick to draw crude diagrams on the aircraft's freshly painted fuselage. The gathered pilots, most under 25 years old, many with less than 40 hours of flying experience, watched intently as Adlam sketched vectors illustrating the problem that had haunted Allied squadrons for the past year. Survival rates among new RFC pilots had reached catastrophic lows, averaging just 11 combat days before being killed or wounded. Something had to change. "Forget everything you think you know about shooting," Adlam declared, his voice carrying across the grass airfield. "When your target is moving across your flight path at 100 miles per hour and you're approaching at 80 miles per hour, aiming directly guarantees missing. You must aim into empty space, where nothing yet exists." This counterintuitive concept, firing at where the enemy would be rather than where they were, represented a fundamental shift in aerial combat philosophy. The breakthrough had come through painful experience and the application of mathematics to warfare. Major Norman Macmillan, who survived 102 combat missions while claiming 11 victories, later documented this transition in his memoir. "I suddenly understood that I needed to shoot at a point in space the enemy had not yet reached. The realization came after watching hundreds of rounds disappear harmlessly behind Fokkers and Albatross scouts." Technical developments followed rapidly. In early 1917, Lieutenant Gilbert Payne developed a crude but effective mechanical sight using brass wire formed into a basic lead computing device. The Payne sight, as it became known informally among RFC pilots, provided 3 reference points at different distances ahead of the enemy aircraft based on estimated crossing angles. At a 90-degree deflection, pilots would aim 3 aircraft lengths ahead of their target. For 45-degree angles, 1.5 lengths. The device improved hit probability by approximately 35% in training exercises. French engineers pursued a parallel approach. Captain René Gasnier, a mathematician before the war, developed a series of trigonometric tables that pilots memorized, converting closure rates and angles into lead distances. Gasnier's method was intellectually sound, but proved impractical in combat, where split-second decisions left no time for mental calculation. The Germans, meanwhile, had been systematically addressing the problem since 1916. Oskar Winkler, working with optical manufacturer Carl Zeiss, had developed the reflex visier, a primitive reflector sight that projected an illuminated aiming point onto a glass screen. Though lacking computing capability, the sight improved aiming consistency and freed pilots from having to focus on iron sights mounted directly on their machine guns. Pilots who mastered these early lead shooting techniques reported dramatic improvements in combat effectiveness. Lieutenant Edward Mick Mannock, who would ultimately claim 61 victories, wrote in his diary on September 18, 1917, "I no longer aim at the Hun, but at a point in empty space ahead of him. Strange that shooting where he isn't proves more effective than shooting where he is. Have destroyed 3 Albatross scouts this week using this method." Not everyone embraced the new techniques. Captain James McCudden, despite his eventual success with 57 confirmed victories, initially rejected lead shooting as theoretical nonsense. In correspondence to his squadron, commander dated October 1917, McCudden wrote, "A true fighter aims at what he can see, not at invisible mathematical points." 3 weeks later, after surviving a near-fatal engagement with Jaster 11, McCudden reversed his position completely. His combat report acknowledged, "I would have been killed had I not employed the deflection methods recently taught. I fired approximately 4 aircraft lengths ahead of the approaching Albatross DV and observed multiple strikes along his fuselage." By late 1917, both Central Powers and Allied air services were developing formal deflection shooting techniques. The transformation had begun, but much remained to be done. Calculating proper lead angles remained largely a matter of pilot judgment and experience, a dangerous learning curve when mistakes meant death. What was needed next were mechanical computing devices that could solve the deflection equation automatically during the chaos of combat. January 12, 1943. Wright Field, Dayton, Ohio. The metallic clicking of precision tools filled the laboratory as Dr. Charles Draper carefully adjusted the miniature gyroscopes inside what would become the most advanced gun sight of World War II. His hands, steady despite the pressure, made microscopic adjustments to components no larger than a dime. The mathematics of interception were finally being solved not by pilots' instincts, but by mechanical computing devices. "We are building artificial brains," Draper explained to visiting Air Corps officers. The K-14 computing gun sight performs trigonometric calculations in real time that would take a mathematician with pencil and paper several minutes. The evolution of gun sights had accelerated dramatically since those early days of World War I. After the war ended in 1918, development continued as engineers recognized the fundamental problem remained unsolved. The British Barr and Stroud GM2 gun sight of 1935 represented the first major breakthrough. Using a simple mechanical calculator, the GM2 allowed pilots to set their target's wingspan and estimated range. The sight then adjusted its projected aiming point to account for basic deflection. German engineers pursued parallel development. The Revi 16B reflector sight, installed in the Messerschmitt Bf 109E fighter, established new standards for clarity and brightness. The illuminated reticle appeared to float in space ahead of the aircraft, allowing pilots to keep their eyes focused at infinity while tracking targets. What the Revi lacked in computing ability, it made up for in optical quality. Dr. Draper's team at MIT combined these approaches with American engineering precision. The resulting K-14 gun sight contained miniature gyroscopes that sensed the fighter's rate of turn. This data fed into a mechanical computer weighing just 7 pounds, but capable of solving complex deflection problems instantaneously. To use the K-14, a pilot first identified his target's wingspan using adjustable brackets in the sight picture. This input, combined with the aircraft's own movement detected by the gyroscopes, automatically calculated the required lead angle. The illuminated aiming point shifted position accordingly, showing exactly where the pilot should aim to hit a moving target. The technical specifications were impressive for 1943 technology. The K-14 operated on 24-volt aircraft power, weighed 64 pounds including all components, and functioned reliably in temperatures from -40 to +120 degrees Fahrenheit. Its gyroscope spun at 12,000 RPM, powered by electric motors barely larger than a matchbox. The optical glass was specially coated to prevent fogging and maximize light transmission under all conditions. Japanese engineers created their own Type 98 reflector sight for the A6M0 fighter. The device was simpler than Allied counterparts, but matched perfectly with Japanese naval aviation doctrine, emphasizing turning dogfights. It projected a fixed reticle pattern of concentric rings, requiring pilots to make mental lead calculations. Captain David McCampbell, who would become the U.S. Navy's highest-scoring ace with 34 victories, later described his first experience with computing gun sights. "It went against everything I had learned. I had to force myself to aim where the sight indicated rather than where my eyes and brain told me to aim." My first combat using the system ended with 2 confirmed kills on my first firing pass. The psychological challenge remained significant. Pilots had to trust their instruments over instinct, firing at empty air with faith that physics and mathematics would guide their bullets to targets. Training programs evolved to help pilots make this mental adjustment. British instructors at the Empire Central Flying School developed the shadow aircraft method. Student pilots practiced against specially marked target aircraft, gradually learning to trust their computing gun sights rather than visual instinct. Hit probabilities in training exercises improved from 2% to over 35% after just 10 training sorties. Colonel Hubert Zemke, commanding the 56th Fighter Group equipped with Republic P-47 Thunderbolts, mandated 2 weeks of intensive gunnery training with the new K-14 sights before allowing pilots into combat. His directive to pilots was unambiguous. Trust the sight. If you aim where you think the enemy is, you will miss. If you aim where the sight tells you, you will destroy him. By mid-1943, the engineering challenge had largely been solved. The next test would come in actual combat, where these computing sights would face the ultimate evaluation against experienced enemy pilots fighting for their lives. March 14, 1944. Skies over Berlin, Germany. The gun camera footage jerked slightly as Captain John Godfrey's P-51 Mustang closed rapidly on the Focke-Wulf 190. Through his K-14 gun sight, Godfrey observed the illuminated reticle floating seemingly impossibly far ahead of the German fighter. His thumb hesitated momentarily over the firing button. Every instinct screamed to aim directly at the enemy aircraft, but training overrode instinct. Godfrey forced himself to keep the Pipper exactly where the computing sight positioned it, apparently in empty air. 6.50 caliber Browning machine guns erupted simultaneously, each firing at 750 rounds per minute. The tracers appeared to stream harmlessly ahead of the FW-190, yet 3 seconds later, the German fighter shuddered violently as multiple 500-grain bullets tore through its engine cowling and cockpit. The computing sight had performed its calculations perfectly, solving in milliseconds an equation that factored closure rate, deflection angle, bullet time of flight, and relative motion. This engagement, documented in Godfrey's combat report and preserved on 16mm gun camera film, demonstrated the revolutionary impact of computing gun sights on aerial combat effectiveness. Before introduction of the K-14 sight, average 8th Air Force fighter pilots expended approximately 4,500 rounds for each enemy aircraft destroyed. After K-14 implementation in early 1944, ammunition expenditure dropped to 1,800 rounds per victory, a 250% improvement in combat efficiency. The statistical validation extended across all theaters. The 348th Fighter Group operating P-47 Thunderbolts in the Pacific Theater reported kill probability increases from 8% to 31% after converting to computing gun sights. The RAF's number. 132 Squadron Flying Spitfire MKIXS, equipped with gyro-stabilized gun sights, achieved 27 confirmed victories during Operation Overlord while expending 73% less ammunition compared to similarly experienced squadrons using earlier reflector sights. Lieutenant Colonel Francis Gabreski, who would finish the war with 28 aerial victories, described the psychological barrier pilots faced. "You had to trust mathematics over instinct. Your brain screamed to shoot at the aircraft you could see, while the sight told you to aim at empty space. The hardest part wasn't technical, it was learning to override your natural reflexes." Training methods evolved to overcome this barrier. The 56th Fighter Group implemented a progressive training regimen requiring pilots to practice deflection shooting for 15 hours in modified AT-6 trainers before transitioning to combat aircraft. These trainers featured camera guns synchronized with gun sights, allowing instructors to review film footage and correct aiming errors. British and American approaches differed subtly in implementation. RAF pilots using the MKIIS gyroscopic sight were taught to maintain a steady turn rate while tracking their target, allowing the gyroscopes to calculate lead automatically. USAAF pilots with the K-14 learned to fly the dot, keeping the illuminated aiming point on target while the aircraft turned underneath them. By mid-1944, the lead computing gun sight had fundamentally transformed aerial combat. Pilots no longer aimed at what they could see. but at what mathematics told them would intercept their target. The counterintuitive concept of aiming past the enemy had evolved from desperate improvisation to engineered precision, and pilots who mastered the technique rarely missed again. May 17, 1944. 357th Fighter Group, Leiston Airfield, England. The formation tactics that had dominated air combat since World War I underwent radical transformation as computing gun sights reached operational squadrons. Major Leonard Kit Carson stood before a chalkboard in the briefing hut, sketching new attack patterns that exploited the K-14's capabilities. The room smelled of cigarette smoke and damp wool as pilots leaned forward on wooden benches, studying diagrams that contradicted everything they'd previously been taught. "Gentlemen, forget the Loughbury Circle," Carson announced, referencing the defensive wheel formation developed in 1917. "With computing gun sights, we no longer need to maneuver directly behind the enemy. The old doctrine of getting on his 6 o'clock is obsolete." This tactical revolution spread rapidly across Allied fighter groups. The traditional pursuit curves, attempting to match an opponent's flight path to achieve a firing position directly behind them, gave way to high-angle deflection attacks that maximized closure rates and minimized exposure to defensive fire. Fighter pilots began approaching targets at angles between 30 and 60 degrees, using their computing gun sights to determine the necessary lead. Statistical analysis from the 8th Air Force's Operations Research Section confirmed the effectiveness of these new tactics. Engagement analysis covering March through June 1944 documented success rates of 37% for high-angle deflection attacks using computing gun sights, compared to 19% for traditional tail chase approaches. Luftwaffe pilots developed countermeasures rapidly, having observed the new Allied tactics. By mid-1944, German fighter units were trained to execute violent, unpredictable maneuvers when Allied fighters approached at high deflection angles. The standard German response became the Saint-Cyr, snake pull, a rapid rolling pull-up combined with throttle reduction that often caused Allied pilots to overshoot their calculated lead point. The tactical chess match intensified through late 1944. Allied pilots learned to anticipate the German counter-tactics, using the computing sights to rapidly recalculate as target aircraft maneuvered. Lieutenant Richard Bong, who would finish the war as America's highest-scoring ace with 40 victories, described this evolution in a debriefing on October 12, 1944. "I don't aim where the enemy is, or even where he's going to be. I aim where he'll be if he makes the evasive maneuver I expect him to make when he spots my attack." Training programs evolved to match the tactical changes. The 31st Fighter Group instituted shadow training, where instructors flew mock combat at progressively increasing deflection angles, gradually building pilot confidence in their gun sights. After implementing this program, the group's kill-to-sortie ratio improved by 47% during the final months of 1944. Captain Charles "Chuck" Yeager, who would score 11.5 victories before becoming famous for breaking the sound barrier, developed his own training method he called leading the leader. In this exercise, paired aircraft would fly line abreast, with the wingman practicing calculated leads against the leader's aircraft using camera guns. Yeager's technique produced pilots who could accurately estimate deflection angles without relying solely on instrument guidance. By early 1945, the revolution was complete. High-angle deflection shooting using computing gun sights had transformed air combat from an instinctive art to a calculated science. Pilots no longer aimed at what they could see, but at invisible intercept points calculated by precision instruments. The days of missing the enemy were over. The age of mathematical gunnery had arrived. June 8, 1952. Edwards Air Force Base, California. The desert sun reflected harshly off the canopy of the F-86 Sabre as Major John Glenn examined the A-1CM gun sight mounted in his cockpit. The principles developed during World War II had evolved into increasingly sophisticated systems, yet the fundamental physics remained unchanged. In the jet age, where closure rates now exceeded 1,000 miles per hour, computing the lead angle had become even more critical and more complex. "The mathematics haven't changed," Glenn explained to a visiting congressional delegation touring the base. "We're still solving the same intercept problem, but now at transonic speeds. The A1CM contains miniaturized components that would have filled an entire room in 1943. The evolution of lead computing gun sights continued through the Korean War, where pilots faced the sobering reality that despite technological advances, the challenges of high-speed deflection shooting remained. The MiG-15 jets flown by Soviet and Chinese pilots proved elusive targets, capable of rapid acceleration and tight turning radii that could confound even the most advanced computing systems. Colonel Harrison Thing, commanding the 4th Fighter Interceptor Wing, instituted mandatory deflection gunnery training after early engagements revealed many pilots reverted to instinctive direct aiming during the stress of combat. His training directive, dated August 17, 1951, specified, "All pilots will practice high-angle deflection attacks daily using camera guns and computing gun sights. There will be no exceptions." By 1955, the integration of radar with computing gun sights created the first truly automated fire control systems. The AN/ASG-15 radar ranging gun sight, installed in late-model F-86H Sabres, calculated target range automatically rather than requiring pilot input. The system reduced pilot workload while increasing first-pass hit probability by 43% in controlled tests at Nellis Air Force Base. The principles pioneered in propeller-driven aircraft transferred directly to modern head-up display systems. Captain Charles Maltzby, who flew 361 combat missions in Vietnam in FA-4 Phantoms, observed, "The FA-4's lead computing optical sight fundamentally works on the same principles as World War II gun sights. The computers are faster and more precise, but we're still solving the same problem, intercepting a moving target from a moving platform." Modern fighter aircraft like the F-15 Eagle and F-16 Fighting Falcon incorporate sophisticated digital fire control computers that perform thousands of calculations per second, yet the fundamental concept remains unchanged from what those early World War I pilots discovered through painful experience. The pilot still aims at empty space where nothing yet exists, trusting the computer's calculations rather than visual instinct. Training methods evolved to match technological sophistication. The US Navy's Top Gun program, established in 1969, emphasized deflection shooting techniques specifically designed for high-performance jet aircraft. Instructors taught a concept called running the solution, continuously updating the firing solution as both aircraft maneuvered, releasing weapons at the precise moment when the computer indicated maximum probability of hit. The mental leap required of those early aviators, aiming at empty space rather than visible targets, remains a fundamental challenge for each new generation of fighter pilots. As Lieutenant Colonel Dick Anderegg, who flew F-4s and F-15s before becoming an Air Force historian, reflected, "The most difficult aspect of aerial gunnery isn't technological but psychological. Every instinct tells you to aim at what you can see. The disciplined fighter pilot overcomes that instinct and trusts mathematics instead." The triumph of analysis over instinct, of calculation over intuition, represents one of aviation's most significant transformations. What began with crude estimates and hand-drawn diagrams evolved into sophisticated digital systems, yet the central insight remains unchanged. To hit a moving target from a moving platform, you must aim where your target will be, not where it is. By learning to aim past the enemy, pilots finally stopped missing, and aerial combat was forever transformed.